Hello, this is Arzu Rajabi. Today I'm going to present our work on the practically or impracticality of adversarial perturbation for image privacy. This work has been done when I was a PhD student at Oregon State University, and to do this project I collaborated with the Portland State University. In this paper, we focus on image privacy threats, and the reason is that recently we faced different image privacy violations. And one of these violations that we can mention is reverse image search. As an example, an adversary can use Clearview API to find all of your social accounts or your personal website by using one of your photos. The other image privacy threat we can mention to unauthorized image classification. Recently, a framework has been proposed which called KPIC. This framework uses face recognition and face detection models to track your relationship using your social networks images. In this paper, we especially focus on unauthorized automated face recognition models. And the reason is that there are billions of available images, and an adversary can use GPUs, Azure, or AWS to learn very large and high accurate face recognition models. And we focus on image sharing platforms, especially because they already have access to our images, and they have the resources to learn face recognition models, so they can easily track our relationships or activities. As we said, we focus on the face recognition models in this paper, and the reason is that in the past, for example, in 1991, the best face recognition models achieved at most 60% accuracy on large data sets. But now, recently, with the advent of very complicated and advanced machine learning algorithms, for example, deep learning, one can learn a kind of deep neural networks on the large datasets and achieve high accuracy. As an example, recently deepfakes achieved more than 97% accuracy on LFW dataset, and LFW dataset actually contains more than thousands of the images of celebrities. And what these deep neural networks are? Actually, deep neural networks for the images are convolutional neural networks. The convolutional neural networks are constructed with different layers, and these layers are convolutional layers, max pooling, and some fully connected layers. Despite the high accuracy of convolutional neural networks or CNNs, they are vulnerable to adversarial examples. And adversarial examples are benign example or images with adversarial noise. Adversarial noise is trained on a target CNN. And as you can see in this image, we can fool a target CNN just by adding less than 1% of the adversarial noise, the image in the middle that trained on the target CNN. The adversarial examples have two nice properties. The first one is that these images are recognizable for humans but not CNNs, and also they can be trained for transferability. That means that adversarial examples can be trained on the CNN A such that they are able to fool other CNNs, for example, CNN B. Because of nice properties of adversarial perturbation, they have been considered as a potential defense for image privacy. And recently, a method has been proposed based on the adversarial examples that suggests a user to perturb her images before posting or sharing them. But the problem with this approach is that this approach assumes a user has access to the target CNNs, and also the users need to learn one perturbation for every image, which is not practical for the real application. Also, we have seen two nice other adversarial-based schemes for image privacy in this session, but they are trying to solve other problems, and they are not suitable for image sharing platforms. So before introducing our approaches, we identify some practical requirements for adversarial-based approaches that designed especially for image sharing platforms. The first requirement is black box setting. It means that a user doesn't have any knowledge about the target CNNs, and users don't have a very large data set, or they don't want to share their images with a third party for learning a CNN or a perturbation. Also, they want to recover their images, and they don't want to have a kind of one perturbation per image for recoverability. Also, they want to have a recognizable image, so they can browse their image, or they can search over their images. And also, these approaches should be able to work with the current or existing platforms. The first approach that we propose called Universal Ensemble Perturbation, or UAP. Universal ensemble perturbation learns a perturbation over a small CNN, so it's computationally inexpensive. Also, this approach learns perturbation over multiple CNNs and several images to provide transferability, and this approach can fool unknown CNNs. This approach adds a perturbation to arctangential hyperbolic space of the image, so we can recover the image with the minimum loss. And this approach just learn one perturbation for several images. It means that we don't need to save one perturbation per image. So this approach actually meets the practical requirements. To learn universal ensemble perturbation, we use 3 CNNs, and we learned this perturbation over 200 images. We extended colony attack to support ensemble and universal learning, and then we'll learn a minimum perturbation that can fool all these 3 CNNs. Then we add this perturbation to the arctangential hyperbolic space of the image with the different levels, and these levels defined with the beta values. For example, when beta is equal to 3, it means we add 3 times more perturbation compared to when the beta is equal to 1. Increasing these parameter beta values leads the transferability increases. To evaluate our UEP approach, we use 3 different models. So the first one is Google Vision API face detection model, which is an online model. And the second one is Clarify face detection and face recognition model, and these models are online as well. And we use an offline model that's called Deep Face, and it has face detection and face recognition models as well. As you can see, we evaluated our UEP for different beta values, and for beta equal to 3, we can see that the transferability is high, and we can fool face recognition models very well. And we found that for fooling the face detection models is really hard, but as long as we can fool face recognition models, we can provide some level of privacy. We also considered different potential attacks against UEP, and we found that the perturbation estimation and removal is the most effective one. In this attack, an attacker assumes that the perturbation is added directly to pixels value, and attacker can use the median function to estimate UEP. For example, if the UEP has if the adversary has access to the multiple perturbed images, so she can estimate the perturbation UEP just by using the median function. You can see the estimated UEP in the second image from the left. By inversing this estimated UEP and add it to the perturbed image, an adversary can recover some image that is classifiable for the classifiers. This image is not exactly this original one, but good enough for classification. The problem with the UEP is that we use a single perturbation for several images, so it's not secure. And the solution is that we have to use a unique perturbation per image, and it's not practical. To address this problem, we came up with another idea, and the new approach is called K-randomized transparent image overlay, or KRTIO. So transparent overlay images for the first time has been proposed to fool online video classifiers in which there is a kind of source image and an overlay image, and the overlay image will be added to the source image with the weight of alpha. So for example, if the weight of if the alpha is equal to zero point 0.7, it means that 70% of the image comes from the source image and 30% of the perturbed image comes from the overlay image. And here, for example, the picture of the car is an overlay image, and the picture of the face is a source image. This approach, unfortunately, is vulnerable to blind signal separation when we use one overlay image for several images. If we want to save one overlay per image, this approach can be used for image privacy, but it's not practical since we need to save one perturbation per image. To address this problem, we came up with a new idea that's called the K-randomized transparent image overlays, or KRTIO. This approach generates a unique overlay image just by using a few overlay images and a secret key. Let's assume that we have a set of overlay images and we want to generate a unique overlay image for a source image. This approach uses the idea of a source image and a secret key to select K overlay images. Let's assume K is equal to 2. After selecting two overlay images, this approach divides the images to some blocks and permutes the blocks just by using the idea of the overlay image and the secret key. After permuting the blocks, this approach computes the average of the overlay image and added this average of the overlay image with the weight of alpha to the source image. Here we presented different perturbed image with KRTIO approach. On the right, you can see the image that perturbed with the different K values and block sizes for the fixed alpha, which is equal to 2.5. As you can see, increasing the K values leads that the final image to look like a noisy image, and the noisy image, the random noise doesn't work on CNNs. On the left, you can see that images that perturb with the different alpha values and block size, and for the K equal to 3. As you can see, increasing the alpha values improves the recognizability of the images. To evaluate KRTIO approach, we evaluated this approach against Google Vision API face detection model. As you can see, for a K equal to 8, we couldn't fool this model very well. But for the K equal to 3 and the small values for block size and alpha, we can fool this model very well. Also, we evaluated KRTIO against clarify face detection and face recognition models. As you can see, for a small value of the block size and the alpha, and when the K equal to 3, we can fool the face recognition models very well. But we couldn't fool the face detection model. We also evaluated KRTIO against the deep face recognition and face detection models. As you can see, again, for the small value of the block size and the alpha values, we could fool this model very well, in both face detection and face recognition models. Here we consider different potential attacks against KRTIO. The first potential attack could be improving image quality using filtering techniques, and the second one is training a robust CNNs on both BNN and KRTIO perturbed images. The first approach, which is using filtering techniques, is computationally inexpensive because the adversary doesn't need to retrain her models. And we found that we tried different filtering techniques, and we found that these techniques couldn't improve the face recognition models performance, but for some hyperparameters, these techniques could improve the face detection models performance. The second approach, which is the training a robust CNN, an adversary needs to retrain a new model on both KRTIO and benign images. So when an adversary returns a robust CNNs, she can improve her CNNs accuracy by 15 to 20%. But this approach is computationally expensive, and also it doesn't guarantee robustness for other type of adversarial examples. In this paper, we first identified the practical requirement for adversarial-based image privacy approaches that's designed for image sharing platforms. And we propose a learning-based image adversarial perturbation called UEP, and other one is a semantic-based adversarial perturbation called KRTIO for image privacy. And we observed that the semantic-based adversarial perturbation KRTIO is computationally inexpensive and can fool unknown CNNs. And also, this approach is more robust against different type of attacks. Thank you so much for listening to my presentation. If you have any question, I would be happy to take them. Also, you can send your question to my email or to Dr. Rakesh Buba.